Alright, so in today's video, we're diving deep into one of the most essential tools in modern chemistry: nuclear magnetic resonance, NMR, spectroscopy. This technique is an incredibly powerful way to identify unknown compounds, study their structure, and even explore molecular dynamics. We'll primarily focus on proton NMR, or 1H NMR, which is widely used to analyze hydrogen atoms in organic compounds. By the end of this video, you'll understand how NMR works, how we interpret spectra, and why this technique is so valuable, not just in chemistry labs, but also in medical applications like MRI scans. Let's get started. Before diving into NMR specifically, let's quickly cover what spectroscopy is. Spectroscopy is a broad technique that measures the energy differences between possible molecular states by analyzing the frequencies of electromagnetic radiation absorbed by molecules. In simpler terms, when molecules interact with light or other forms of energy, they absorb specific amounts, depending on their structure. This absorption provides valuable information about the molecule's characteristics. For instance, different spectroscopic techniques, such as infrared, IR, ultraviolet, UV, and NMR, focus on different types of energy interactions and molecular properties. NMR spectroscopy is unique because it focuses on nuclear spin transitions, a form of energy unique to the nuclei of atoms, particularly protons and other nuclei that possess magnetic moments, and this makes NMR a key tool for determining molecular structures. Now, let's get into the heart of the topic: NMR spectroscopy. At its core, NMR relies on the fact that atomic nuclei, especially those with odd numbers of protons or neutrons, act like tiny magnets. When these nuclei are placed in a strong magnetic field, they align either with or against the field, creating distinct energy levels. When we apply a pulse of radio frequency, RF radiation, to the sample, the nuclei absorb the energy and shift from a lower energy state to a higher one. Once the RF pulse is removed, the nuclei release this energy as they return to their original state. This release of energy can be detected and converted into a spectrum. The resulting spectrum is a graph that tells us a lot about the chemical environment around specific atoms in a molecule. The position of each signal, known as the chemical shift, provides clues about the types of atoms present, while the splitting patterns and intensity of the signals give us insights into the structure of the molecule. Now, let's narrow our focus to proton NMR, or 1H NMR, which is one of the most widely used forms of NMR spectroscopy. In this technique, we're analyzing hydrogen nuclei, or protons, because hydrogen is present in most organic molecules and its signal is easy to detect. In proton NMR, the chemical shift of the hydrogen atoms reveals the type of chemical environment they're in. For example, protons attach to different functional groups, like alkanes, alcohols, or aromatic rings, produce signals in different regions of the spectrum. When looking at an NMR spectrum, there are three key pieces of information you should focus on. Chemical shifts. This is the position of the signals along the x-axis, measured in parts per million, ppm. Chemical shifts provide insights into the magnetic environment of the hydrogen atoms in a molecule. For example, protons and alkanes typically appear between 0.9 and 1.5 ppm, while those attached to double bonds, like alkenes, appear further downfield, around 4.5 to 6.0 ppm. Integration. This represents the area under each peak, which tells us how many protons are contributing to that signal. So, if a peak has twice the area of another, it means there are twice as many protons in that environment. Multiplicity, or splitting patterns. The splitting of signals into doublets, triplets, or quartets provides clues about how many neighboring protons are nearby. This phenomenon is known as spin-spin coupling, and it occurs because protons in nearby environments can influence each other's magnetic fields. For instance, a proton with two neighboring protons will appear as a triplet, and one with three neighboring protons will show up as a quartet. These patterns are incredibly useful when piecing together the structure of a molecule. It's important to have a good understanding of where different functional groups typically appear on an NMR spectrum. Here's a quick overview of some common ones. Alkanes, 0.9, 1.5 ppm. Alcohols, OH, 1.0, 5.0 pm, depending on the hydrogen bonding. Alkenes, 4.5, 6.0 pm. Aromatic rings, 6.0, 8.5 ppm. Carboxylic acids, 10.0, 12.0 pm. By knowing the approximate ranges for these chemical shifts, we can start to deduce the types of groups present in a compound. For example, if you see a peak around 9.5 ppm, it's likely from an aldehyde proton. Let's take a deeper look into spin-spin coupling. This phenomenon occurs because the magnetic field experienced by a proton is influenced by the spins of neighboring protons. As a result, the NMR signals split into patterns, like doublets, triplets, or quartets, depending on the number of neighboring protons. The rule is simple. A proton will split into n plus 1 peaks, where n is the number of adjacent protons. So if a proton has 2 neighboring protons, it will appear as a triplet. This type of splitting helps chemists determine the connectivity between atoms in a molecule. For example, if you see a triplet and a quartet next to each other, you might suspect that these signals come from a CH2-CH3 group. While NMR spectroscopy is an indispensable tool in organic chemistry labs, it's also widely used in medicine. In fact, magnetic resonance imaging, MRI, is essentially a large-scale application of 1H NMR. MRI scanners measure the NMR signals of water molecules in different tissues of the body and convert these signals into detailed images, which are crucial for diagnosing diseases. MRI is particularly effective at visualizing soft tissues like muscles, the brain, and organs, making it an invaluable tool in the medical field. It's just one example of how NMR principles extend beyond the lab and into real-world applications. Alright, let's recap the most important points from today's video. NMR spectroscopy measures the energy differences between nuclear spin states, giving us detailed information about molecular structure. Proton NMR, which H NMR, focuses on hydrogen nuclei and provides valuable data about the chemical environment of protons in a molecule. Chemical shifts, integration, and spin-spin coupling are the 3 key pieces of information we use to interpret NMR spectra. The practical applications of NMR range from identifying molecular structures in the lab to imaging human tissues with MRI. If you found this video helpful, don't forget to like, subscribe, and share it with your friends. For more in-depth learning resources, be sure to check out King of the Curve. Thanks for watching, and good luck with your studies.